In this lecture, we'll look at an example of a non-reentrant exception handler. Remember that a non-reentrant exception handler is an exception handler in which you do not allow other exceptions to occur while you are handling one exception. Let's start with the problem statement. Let's say that someone asks us to write an exception handler that prints the address of the instruction that has caused the exception and also prints the cause of the exception. We'll assume that there is a data area that's reserved for usage in this exception handler, and the address of this data area has been placed in the U-Scratch register, which is CSR 0x040 at the initialization. In the previous lecture, when I recorded the video, I had the saving in the systems register that was 0x140, and I only realized that after recording the video, so I fixed that into the slides. But you'd be using the systems register if you're writing a system level exception when you use the user register, the US Scratch, if you're writing a user level exception. The first thing that we need to do in order to implement this handler is to save the registers that we're going to be using in the handler. As I mentioned before, when you are writing a handler, you must save all the registers that you use in the handler. It's not only the S registers, because when you come back from the exception, the application that was running expects that none of the values of any of the registers has changed while you are executing, while the exception was being handled. So here's a model. We have the control and stats register. The only one that we care about for saving the registers is the US Scratch register. And then I have the registers in the CPU that I'm going to use in the handler will be A0, A1, T0, and T1. And I just put some values in there so that we can work with this example. But what's going to happen is that when an exception happens, the registers, all the registers of the processor may contain any value. And the rule that you have to follow is that once you finish executing the exception handler, all those values must be the same that they were when the exception occurred. And then we have memory. We have an area of memory that has been reserved for the exception handler. And what we get is the address of the first byte of this area. So saving the values here will be different than saving the values if I'm using a stack and the stack pointer. So the first thing that I'm going to do is to swap, and I'm going to repeat the animation so that you can see what's going on. So let's first look at the instruction. The instruction that I'm using is the control and stats registers read-write instruction. And what that instruction will do is take the value that is in this first register, take the value that's in the control register and put into this first register, and then take the value from the second register and put in the control registers. Because this first register is the same as the second register, this will be the equivalent of swapping the two values. So I'm gonna go back one slide so that you can watch now what's happening in the animation. You have the value in the U-Scratch register, you have the value 2000, 2000, which means that the area of memory that has been reserved for my exception handler is this area here. And in A0, you have the value 0x00FFFFC. So let's see what happens when I execute this instruction. The two values are swapped in this way, and this happens atomically. This operation cannot be interrupted by anything. So now we have the value of the address of the first position of this area that has been reserved for my exception handler in A0. So now I can start accessing this area of memory based on this value of A0, which I got from the U-Scratch register. So next what I'm going to do is to save the registers that I'm going to use in the exception handler, except for A0, because remember my A0 is now in my scratch register. This value that I have in A0 is actually the address of the first position of the area of memory that I'm going to use. So first I'm going to start T0 into that first position. Then I'm going to start T1 into the next position. And then I'm going to store A1 into the next position. And now what I'm going to do is to copy the user A0, which is in the U scratch register, into T0. And notice that this is safe now because the value that was in T0 has already been put into memory in a safe position. So it is safe now for me to write over the value of T0. So that's what I'm going to do. And now that I have the value, the original value that was in A0 is in T0, what I'm going to do now is simply to write that value into another memory position. So this is my A0. So I have now here is what was in T0, T1, A0, A1 and A0. So this is how I save the registers before I start executing my exception handler. So now I am in my exception handler. There is the cause registers that contains the bits 0 to 31. And the handler will have to save any register that the handler uses. We already did that. Now we're going to put 0 into T1. So T1 is equal 0. And now I'll move the cause to T0 and I'll clear the cause for the exception. So by doing this read-write instruction again, so I exchanging the value. So what this instruction I'm going to do is take the value of the control and status register 42, which is the cause register, and put that into T0. And it will going to take the value that's currently in T1, which is 0, and put into that control register. What the effect of this is that I take the cause out of the cause register, copy that into T0, and I make the cause register equal 0. That's what we call clear the cause. Next, I'm going to write the value 0x7FFF, that is all bits are 1 except for the bit 31, into T1. And then I'll do an AND with the value that I got from the cause. And this will allow me to extract the exception code field without the bit 31. So basically I am masking out the bit 31 because the bit 31 is only used to indicate whether it was an exception or whether it was an interruption. Therefore the bit 31 is not part of the code for the cause. And now I'll say that if this value is 0, so if the exception code was 0, then I'm done. There's nothing for me to do. I'm only interested in the cases where the exception code is not 0. And next, I'll move the cause into A0 because I'm going to use a function call, and the function call to print the value. And now I'll move the exception program counter into A1. So the exception program counter is 041. And this is the CSR RSI that is the read and set immediate, and I use an immediate of 0 here, which means that no bits are going to be set. So that's a way to simply copy a value, one of the control status registers, into one of your registers, is to use, for example, one of the set instructions, but then specify no bits to be set, because then the original register is not changed. So this gives me the address of the instruction that caused the exception into A1. And now I'm going to call print, and print will print the exception error messages. And once I have done that, that's all I have to do. Actually, that was the work that I had to do, was to print the cause and the exception, and I have assumed that I have a print exception function that does that. Once I have done that, then the next job that I have to do is to return from the exception. Before returning from the exception, the handler must clear the cause register, which we already have done. And then it has to restore the stack. It has to restore any registers that it has used. In our example, we are not using a stack. It has what we have to do is to restore from that area that we reserved for the handler. We're going to restore the registers. So I'm going to restore any registers that it has used. And then I'm going to execute the uret exception return instruction. And the uret, we're going to copy the value of the user exception program counter into the program counter, and we'll continue the execution. So here's what I do when I'm done. First, I will copy the value of the exception program counter into T0. And again, I'm using the set immediate version of the read instruction and providing the value 0, so none of the bits are set. And then I will increment that value by 4 because I don't want to go back and execute exactly the same instruction that has caused the exception. Otherwise, for example, if that instruction was, say, a division by 0, if I go back and try to execute that very same instruction again, what's going to happen is that I'm going to be creating an infinite loop, because executing the very same instruction again will cause the same exception again. And I don't want to do that. So I want to advance the execution to the next instruction. The way I do that is by incrementing the exception program counter by 4. So T0 has the new value of the program counter that I have to execute. And then I will write this incremented value to the exception program counter. So this is a read-write instruction. So what this does is takes the value that is in the current exception program counter and puts into T1, and takes the value that's in T0 and puts into the exception program counter. So this is how I restore the program counter. And then now I need to load the registers that I had saved before. So first I'm gonna get the address of that area of memory where I save my data, so my itrap data into A0. And next I'm gonna load back the values that I had stored. I think there's a typo in this slide. That should be a 12. That should be a 0 according to my previous code. I'll fix that. And then the next instruction is CSR write instruction, which you're going to write the value of the A0 into U-Scratch. No, this actually was a 12 in my example. I'll fix that. And then I'm going to now load from 0A0 the value of T0, load from 4A0 the value of T1, load from 8A0 the value of A1. And now I can swap the U-Scratch and the A0 register. So this is exactly what I had done before with that animation, but now I'm doing in reverse order. So this is the case where now I'm swapping between the U-Scratch register and the user A0. And then I can execute the return instruction, the returns from the exception. So again, there is a typo in this slide here. We're going to go back to where we did the saving. And we're going to notice two things that I want to note. First of all, the value of A0 is actually in 12, not 16. I'll fix that. But the other thing that I wanted to emphasize now is why this is not a reentrant code. Because, you know, this code works perfectly fine, and this type of code would work fine in your lab too, because you're not required to write a reentrant exception handler. But let's look at why this is not a reentrant exception handler. If I had enabled the exceptions as soon as I did the save, so if at this point in the code I say now I'm going to enable exceptions so that they can happen while I'm doing my print, If a second exception were to happen at that point, that second exception would bring me to this point here, where I would again take the value that is in the uScratch. Actually, in this case, the value in uScratch would be incorrect. But if I had restored the value of uScratch before enable exception, I would take the value of uScratch. And for this new exception that happened, I would be taking the values of A0, A1, T0, and T1, and I will be overwriting these values here because I only have one position for T0 in this data structure. All T0s always go in this position, no matter which exception I'm handling. That's why this is not a reentrant exception handler. I have to keep the exceptions disabled for this code to work correctly.